Hello, welcome to the YouTube Live. I see a couple people here, and while we wait for others to join, go ahead and set up your windows. That's what I'm doing. Setting up my 3 windows so that I can do polls, see responses, and also see the stream at the same time. I'll turn on the who's here question so that can get us started. So you're going to see your first poll come up. Who's here? And see response window here. Hi, Cody. Welcome. Glad you could make it today. Also, don't forget, I guess I should have mentioned this when I was in Zoom, dang it. Don't forget that you can also, if you have a Gmail account or a YouTube account, you can log in, and then you should be able to participate in this live chat on the side. And that's kind of a way to get, that way you can enter, no matter what type of poll we're on, you can just type stuff in if you want to have a conversation on there. Right. See if anybody's on there. I can't tell if there's people on that thing or not until they say something. But I just entered a hi into the chat there. And I see some people joining. Welcome, MK. Welcome, Jesse and Marisa and Joe. How's everybody doing? Well, I guess you can't really don't enter that into the poll, but I just saw you, most of you, and hopefully you're doing well. Let's see what degrees it is in here today. Hi, Marisa. Looks like we've got a balmy 49 degrees. Nice. Yeah, so things are getting a little bit warmer for springtime, but sometimes I feel like I'm in a cave because it's like 60 degrees outside and that sun feels so good, but this is just cold in here. But that's okay because we have math to warm us up. And that's what we're going to do. And speaking of warm-ups, I've got a few warm-up questions to start with, which I'll open in a few minutes. But I'm going to give a little more time to see if other viewers want to join. And then I have a couple warm-up questions just for fun. And then we're going to go into our concept sharing. Hi, Joe. Nice to see you on the live chat. And yeah, and we'll go from there. So yeah, feel free to type into the live chat and kind of converse with us that way too, if maybe the right question isn't up at the polls right now. Yeah, we'll just give it 1 or 2 more minutes. We've got 8 viewers so far. Last week we had 15, and so I'm hoping we'll get a few more people. Hi, Rihanna. Nice to see you. And go ahead and feel free to enter your name into the first poll. The first poll is always just who's here, and it makes a word cloud. It's just our warm-up poll. Hi, Jesse. I see a lot of people are now starting to make use of the live chat on the side. We've got 4 students engaged in that. And so if you want to do that, again, we have 9 viewers. So if more people want to log into their YouTube or Google account, hi, Taylor. And hi, Kayla. Then we can have that mechanism too. Hi, Sunny. Yeah, yay! I'm just trying to warm up a little bit in here. I'll do a little exercise. Looking forward to this YouTube live. I'm looking forward to the concept share. And then after we share out some concepts, start to explain them or give examples in our own words. And then maybe the best part for me is to hear what kind of questions remain on the concepts. And so that's the latter half of the polls is like, what kind of questions do you have? Or what sticking points did you get caught up on in this week's reading, so that I can start to alleviate that and explain those out, hopefully, so that everybody feels really ready to start doing the problems. And yeah, I don't know why it's always so cold in here too, except that okay, since you came early, you get to see the College Math Studio secrets. So you can see what's outside the studio doors here. Let's take a look. It's like this big, empty cement space. And so it's kind of like a cave. I'm like back here in this weird space, and there's all sorts of weird stuff over there. And so It's like the heat just doesn't want to make it in here. I don't know. Does that help? Oh, but I did get another light. Remember I had lighting issues? You see that? So that's one of the lights for when you have little chicks, little baby chicks, and you got to keep them warm. And so I stole that from them. Haha. No, just kidding. I have 2 of them. Yeah, so I do have some baby chicks right now staying warm. And then I also have this extra light, which works really great. See, when I shut it off, well, you can't tell a difference, but I see a big difference in here. And so hopefully the board is like a lot more legible this week. I took my week 3 videos with this new light in there. So hopefully that'll make it more visible to you all. Okay, cool. Looks like we've stabilized with about 10 viewers here. So welcome everybody. And I'm going to start with the warm-up questions next. These are just quick questions just for a little bit of fun. First one's multiple choice, and it says, what rhymes with this guy's name? And I'm not going to say his name because I don't want to give it away. Spoiler alert, how to pronounce that name. Some people are saying the quality is really bad, and I hope that that resolves. Maybe it's because I took the, I started like moving the video around, you know, like when I started to show the outside. I feel like when I stream stuff and there's a lot of movement in the video, then it gets like choppier, maybe because there's just more like change in the data. So hopefully when I put it back on the thing and I'm just pointing it at the screen, I think that was probably it. When I started showing around all this different stuff and it changed, there's just more fluctuations for more bits for them to travel through your internet. And so hopefully it goes back to being pretty stable now. Yeah, see, that's why I have this question up, because when you first read the book, especially since we don't have a lecture, and you get to 1.7 and you see this Euler's method, that's the spoiler, is that Euler's name rhymes with Euler, not ruler. It's not Euler. You don't say Euler or Euler or anything like that, even though like other things like eulogy or eugenics starts with the EU and it sounds like you would say Euler, but you don't. I don't know why, but it's pronounced Euler. So that's a spoiler. So there you go. Try to practice at home. Unfortunately, we're not face to face, so I can't hear you say it back. But remember, Euler rhymes with spoiler, and Euler's method is the very first you'll learn in differential equations, and it's a pretty good one. Well, actually the worst when it comes to accuracy and precision, but it's the most bare bones one. It's the classic first thing that people would think of to do, and it is very much analogous to linear approximation, where you just, for Euler's method, you just evaluate the vector field at the current state, and then you assume that the vector field is constant over a fixed amount of time known as dt, and so you multiply the value of x prime times dt, and then you change your state accordingly. That's Euler's method in a nutshell, and there you go. Now, we'll move on to the next question, which I was trying to give you some time to think about in the Zooms, because I thought of half a joke, which is to say I thought of a good start to a joke, but I couldn't think of an answer. Like, why did the chicken cross the road? Why did the trajectory not cross itself? And so that's the one I have here. And I wonder if anybody has a good punchline to that joke. Why did the trajectory not cross itself? I'll draw a picture on the board while I wait for anybody to add in a response. No, I put in a little lesson there. This is one of the things that I forgot to emphasize in my trajectories video. And so that's why I added it in here, because I wanted people I wanted people to make sure that you got this point, which is in section 1.6, and it discusses the fact that trajectories cannot cross. They can't cross themselves. They can't cross each other. They just simply can't cross in the state space. The state space is also known as the phase plane. So I'm going to apologize in advance for using that, but a lot of books refer to that as the phase plane instead of the state space. And anyway, they can't do that little fishy thing that I just drew on the board there. They can't cross themselves because remember that the vector field that's overlaid on top of the state space, the vector field is a function, a proper function. And functions always give a unique output for every input. And so here you can see at any point where a trajectory would either cross itself or cross another trajectory, like for example, right here at this point, that would mean that the vector field is telling me to point in two different ways at the same spot. But that doesn't make any sense because the vector field is a function, right? So we have x prime is equal to f of x. And here I kind of wrote the one-dimensional state equation, but that really generalizes well to two dimensions. So like in two dimensions, I guess rather, I should write it like this. Y prime is equal to g of xy. Right, so if we have some functions f and g, which are telling us which way the vector field's going to point, then when we plug in the current state, like here's the current state right here, x comma y, there's only one value that's going to come out of f and g. There's going to be a unique output for that input. And so the x prime, y prime has to be pointing just in one direction. But if it crossed itself, that would mean that the vector field would be pointing this way for that one, and then it would be pointing that way for the other one. And that would mean that the vector field was giving outputs for the same input. That just can't happen. That can't happen if f and g are properly defined as functions. They'll always give you exactly one output, because then it wouldn't function properly. Exactly. I like that one. Yeah, so I put on brainstorm, so if you want to vote up and down on the little punchlines that are coming in, you can feel free to do so. But the main driver behind me posing that riddle was to emphasize this point. That was an important point in the section, and I'm sorry I excluded it from the video on 1.6, but hopefully that people are starting to get the feel for that. The reason I want to focus on that so much is because that later we start to do analysis of trajectories in the phase plane, and we start to try to make a global picture of all the possible things that can happen for different initial conditions. It's going to be really important that we know that trajectories can't cross themselves or each other. Because, for instance, a closed trajectory, like we saw in the predator-prey model, will then kind of limit where the initial conditions inside of it can go, because they can't really escape being inside of that closed space. So that property, really, it's it's known as the Uniqueness Theorem, mentioned in the book, with some names, but I can't remember the names, but I know it's called the Uniqueness Theorem because it speaks to the uniqueness of the vector fields, because f and g are functions, and so they're giving you a unique output for every input. And so we can't have that wacky behavior. Eventually, trajectories are going to kind of piece out the state space into different basins. If you're peeking ahead, there's a section on basins of attraction. And for work like that, we're going to need to re-emphasize this point. So that's why I brought it up now. And we got a couple responses there. Thank you. It's harder than it looks. I was thinking all night of a good punchline, but I never did come up with anything. Anyway, now time to move on to the main theme of Tuesday's YouTube Lives, which is sharing out our key concepts so that we can start to get an idea of what we want to post for our concept discussion. And remember that concept discussions are more of just like a share out than a discussion. And I don't expect anybody to have to read through them all and give replies. It's not as conversational as the other discussions because you can't view other people's posts before you put your own in. That's because I want everybody to focus on using their own words. And I don't want them to feel obligated to have to, find something that wasn't spoken to yet. Like, I don't want you to look through the list and be like, oh, geez, all the good ones are taken, and now I have to find a concept that hasn't been taken. You don't have to do that at all. It's just which 3 spoke to you as being important from sections 1.5, 1.6, and 1.7. And so here we've got a bunch of entries so far that's starting to form a word cloud, and now I can see the real power of a word cloud. Word cloud's not as good when we're just using it for our names, because actually I don't think anybody has the same name as anyone else in here happens to be. But for this one, I can really see the word trajectories getting really big, and that's one of the biggest concepts for this week. You all caught it. Right. Other things I'm seeing is Euler's method. Remember, spoiler, Euler, it's not Euler's method. Vector fields still, vector fields is a major player this week, and vector fields are the output from the state equations. So they're the values of the change for the states. And vector fields and trajectories go hand in hand because trajectories follow the path of a vector field. You can imagine a vector field being like little arrows drawn on the ground, and you're following them which way to go. Anybody remember Labyrinth, David Bowie's Labyrinth? I love that movie. And like at some point in that movie, the girl's like drawing with like lipstick on the ground. She's like drawing little arrows of which way she's going and trying to follow it. And the monsters mess it up in that movie. But anyway, it just reminds me of that because it's little arrows on the ground that are little arrows in the state space that are being drawn. And then the trajectories just follow along that path. And analytically, they follow along it using infinitely small little steps. So every time I take a step along that line, I'd use an infinitely tiny little step. But realistically, when we try to numerically compute solutions, you can't take an infinitely small step or you'll never get anywhere. And so that's where Euler's method comes in, is that it tells us what size of a step to take. So we're going to take a step of size dt, delta t, that's called the step size. And we're going to exactly step for that long at that constant speed. And then we're going to look down and reevaluate what the vector field says to do now. And then we're going to take another step of that size in that next direction. So hopefully you can start to geometrically appreciate the Euler's method. And this week's reading of trajectories, vector fields, and Euler's method, it's really makes a nice trifecta of learning for this week. They really go well together. Great. Okay, so what I want to do now, which is going to hopefully help people with their concept with their concept post, is explain a concept in your own words. And since the word trajectory is so big here, I'm actually curious to see people try to explain trajectories in your own words and or give an example. This might be easier said than done, but I'm going to move on now, working off of what you all just input to the word cloud. And so I replace the capital word concept with trajectories. Explain trajectories in your own words or give an example. I'm just really curious about how you're going to do it. So I'll stop talking for a little bit because maybe I just explained it in my own words a little bit, but I'd like to see how other people want to describe it. And if you're wondering what to do for your concept post that's due tonight, there's the word cloud right there, and you can pick from any of those. Usually the reading is about 3 sections a week, and so if you even just wanted to not overthink it, you don't have to overthink it or fret about it. you can just use the title of 3 of the sections, because usually I've given you about 3 sections to read. I mean, at least as a starting point for 3 important concepts. Of course, 1 concept per section might be a way to get started on that. So I hope people aren't having that way too heavy on their minds. It's just an early check-in, early on the week on Tuesdays, to make sure that people are engaging with the learning early, because then on Thursdays we move into the exercise set. So we start to put our theory into practice a little bit by doing the exercises. And I want everybody to have completed the readings and maybe hopefully even the videos by then. So that's why I have that check-in there on Tuesdays. I'm getting some great explanations here. One person says trajectories are the path and movement of a point in the state space. And someone else says the path of an object or point as it travels through space as a function of time. Really nice. And then it says a path of where a system has been in time in the state space. Excellent. Yeah. And then somebody says the magnitude and direction a point is going to change given the starting point and function. So that last one where it says the magnitude and direction a point is going to change, that actually sounds more, that reminds me more of a vector field. So if I was to describe a vector field in my own words, I might describe it as a vector, something that has magnitude and direction. And a vector field is that vector where a point's going to change at any given time. And then the trajectory is the actual solution of the dynamics in time as it gets traced out. It follows the vector field. The trajectory follows the path of the vector fields, but they are 2 different things. So this is really great for us to start to talk through these. I really appreciate everybody putting in their own words here so that we can really solidify these concepts. That's how they're related. Yeah, so someone else now has said the trajectory follows the change arrows of the vector field, tracing the path of the state point as it moves through the state space. These are all great. Thank you for contributing these. And these will be up for everybody to see. So if you're watching this even after the live session is ended, this is still some really good stuff to get you ready to submit your concept posts. Yeah, so when everybody's referring to like the movement of a point, usually, not that you have to change your words or anything, but to use more vocab words that are getting built up, the very first point that you start at is usually called the initial condition. So I'm going to write that on the board just because I didn't see anybody use those words, and I want to start to get us all familiar with the vocabulary before I start using it just like as second nature. Okay, so the starting point just to give us a little more words to use, the starting point for a trajectory as it starts to follow the vector field, wherever we first started at, time is equal to 0 usually, is called the initial condition. Now you can think of the condition as a specific value of the states, and initial means starting out. And so that's why the starting point is the same thing as the initial condition. And someone else has just submitted an explanation of trajectory as a solution curve representation of the movement of a system's change through the state space. That one's really nice, I think, because it uses the phrase solution curve. And really what's going on here is that these trajectories are solutions to those equations. So remember, I wrote those equations up there in general, the wherever the functions are that dictate the vector fields for x prime and y prime. Those will have solutions. Like Alan says in his book, almost always, at least for more complicated systems, we're not going to be able to find the analytical expressions, like a mathematical expression for those solutions. Nevertheless, those are the solutions. So at least we can visualize them. And in the case of linear equations, we are going to be able to name the solutions analytically. And so I look forward to that. In chapter 2, we're going to start to get some equations that describe what the solutions are as well. But in this text, we are not overly focused on finding mathematical expressions or doing what's known as analytical methods for solving differential equations. We're going to focus more on what's called the qualitative theory of differential equations. And that's where we see a lot of geometry taking place, and we can visualize it, its movement. And we're going to also practice the numerical aspect of differential equations, where we use numerical algorithms, such as Euler's method, in order to crunch out an approximation to the actual solutions. Actual solutions are usually very difficult to find, but we have lots of algorithms that can approximate them really well. And we have this beautiful geometric space that we can visualize them in. Okay, good. So I think that was a fun practice. Now, I'm going to go on to our last question here, because I don't see a lot of people entering answers anymore to that. And this is just a placeholder. I'm going to leave this last poll question up until it seems like people have gotten enough out of the session, and then I'll close it out. We don't have to stay till 2 if the need's not there. But what I'm putting here is just, what concept would you like me to talk more about? Or what are your questions? And really, this is just a dump zone where you can just put any thoughts or ideas in, and then I can do some board work there. If people want me to start doing exercises, I heard the call from many students for, please, more examples, just more concrete examples worked out. And I don't know if you're ready for that on a Tuesday. I think I plan to do many more of those on a Thursday. But whatever you want to see me do on here, this is your session recorded for you all to learn. So somebody please enter something so I know what to talk about. Otherwise, I'll just give you a friendly wave, and then I'm going to go sit in the sun patch. Ooh, well, come on. That's not fair. Somebody said they want me to talk about trajectories in 4 or more dimensions. I wish I could talk about that better, but 3 space, because we live in a place where we can observe 3 spatial dimensions, 3 spatial dimensions is really the largest dimensional space that we can visualize realistically would be 3 dimensions. So how are we going to deal with trajectories in 4+ dimensions? Certainly, there are tons of models that use more than 4 or more dimensions out there. I've worked with many models like that myself, and what you have to do, unfortunately, is you have to choose which 2 or 3 of those states, of those dimensions that you want to visualize at once, and then you see trajectories moving there, but you can't see them all at once. So you kind of have to pick and choose, or painfully, one time I was working with a model that had about 18 dimensions, and that was a physiologically realistic model of energy production inside a cell that described the dynamics of mitochondria in a cell. I did that when I was a postdoc at UCLA in the medical school, and this is bringing back memories of sitting at my computer with that 18-dimensional system and just being like, what am I going to do? How am I going to picture this? And I would have like a matrix of like all the different states. Like I'd have like 12 graphs popped up in MATLAB at once. And I would try to be looking at the solution of them, trying to track them and find out where the bottleneck of the system was. But it was very difficult. So other things that people want me to talk about are how will Euler's method be used in class? And then somebody said Euler's formula. So I'm not sure if you actually mean Euler's formula, which is related to complex analysis and sines and cosines, or if you meant Euler's method. But I'm going to guess Euler's method because we haven't really spoken about Euler's formula in this program yet. So let's talk a little bit how we're going to use Euler's method in the class. The very first thing we're going to do, and you're going to see that this week, is that you're going to use the online the online vector field plotter that I put the link to in the program, and we're going to find solutions to differential equations that way, because a lot of these models that we're working with, like a complex predator-prey model with maybe logistic growth and maybe different types of interaction between species, the only way we're going to be able to solve something like that, and I'm using these little things for solve because we're not actually solving it, we're going to approximate it using a numerical method. And Euler's method is the go-to method. It's not the only method out there, but it's like the first thing that was thought of to do. And so we're going to practice that by hand. We're going to understand that as an algorithm, and then we're going to use it all quarter long to visualize solutions. To get the idea of what Euler's method is, I'm really going to start saying maybe you should turn it up. Maybe you should switch that little thing, and you'll see this in my video for 1.7. Switch it to Euler's improved method, or switch it to the midpoint rule, or my personal favorite, Runge-Kutta 4-5. That's what I used in the industry when I was a postdoc, and I actually had to solve highly complex equations. I would use Runge-Kutta, which is an extension. All these things are an extension of the classic Euler's method, where people have discovered new and better ways to approximate things more precisely and with less computational time. So like Runge-Kutta, you can get the same results or better with a much larger dt than Euler's method, because Euler's method, you might have to turn the dt down really low, and then you have to take these teeny tiny steps to get an accurate description. So when we actually want to see solutions to complex models, we will probably use a more advanced numerical thing like Runge-Kutta. But because all those numerics are based or originated with the classic Euler's method, that's why that's the first one that students get introduced to. We'll be using it all the time in class, but you won't have to do it by hand like Katherine Johnson did at NASA. You're not going to have to do that the whole time, so that'll be nice. I just want you to be able to understand what you're doing and appreciate the power of the computers we have nowadays. Yeah, so I guess that's a good answer for that, I hope. But keep asking more questions, please, so that I know what you want to talk about. Does anybody else have any other concepts they'd like me to elaborate on, or anything in the book that was confusing? If you've been doing the readings and you want to refer to any page in the book, I've got it in my backpack here, and so I can pull it out and help you answer a question that you'd want to see or respond to any point that was confusing. But for now, I don't really see a lot of action here, so I think that you're all right. That's kind of what I'm assuming, is that you're all right. Does anybody want to give a thumbs up, or like the live video, or give me any kind of sign that you think you don't have anything, no more questions left? Okay, all right. So yeah, I'm feeling a little lonely right now because nobody's saying anything on the chats, nobody's saying anything on the polls. So unfortunately, this isn't as good as a face-to-face class, and it's not going to be the same thing. But I guess I'll have to just roll with the punches of what I'm trying to get input in a lot of different ways, you see. But I'll just have to use what kind of input I get. So some people are saying that they're okay till Thursday on the chat. Some people are saying, struggling to imagine what kinds of examples I ought to use in the concept post for these types of concepts. Yeah, that's really helpful. Let's go with that one. Okay, so let's see, I'm just reading the chat here. A basic overview and breakdown of the predator-prey model. Oh, okay. So somebody's asking to do a little bit of an overview of the predator-prey model, and sure, I'm happy to do that. And someone else is saying that they're struggling on what kind of examples they should use for a concept post for these concepts. And so I can actually speak to that as I go through the predator-prey model, because the examples don't have to be self-created. You don't have to make up an entirely new example. I'll just be checking in to know that you can recognize a concrete example of a concept, and the predator-prey model is going to do that for us. So let me erase the boards. I'll give a little talk about predator-prey modeling, and then I'll point out trajectories, vector fields, what Euler's method would do. I'll point that all out as I go through it. I gotta dry it off too, or it messes the markers up. Okay, so let's talk through predator-prey modeling a little bit more. And this time I'm actually going to use the letters P and V because I caught up with Carrie, my teaching partner, and she, for students who are in the ecology portion, she's planning on presenting this later in the quarter from an ecologist perspective. That's really interesting. This model so many times in differential equation courses, but it was always just kind of for fun, and it wasn't like a real life ecologist using this in practice. So I'm really excited to see how that's going to go. And one simple thing that I got from Carrie already is that in predator-prey models, ecologists are typically using V for the prey because it's the victim, and then P for the predator. Predator and prey both start with P, so we're not going to use P for both. So you see, I've written that up there as V. Hold on, I see a little glare. Hopefully that fixes the glare problem a little bit. Sorry, I didn't recognize that earlier. But the prey is going to be denoted with V because that's the victim of the whole process, okay? And so let's start with the state equations. And so let me build up each term of the state equations and talk through why I'm using that term. So we're going to start with the victim as the first state equation. So that's going to be on the horizontal axis in the two-dimensional state space. And usually the victim or the prey is a type of creature that is thought to have its own food source. Like maybe this is little bunnies. I don't know if anyone else has little bunnies running around outside in the spring, but they've got plenty of little things that they can nibble on, right? And so even though we're not going to model the prey's food explicitly in the modeling process, we're going to assume that the prey always has a nice quality food supply that it can go to. And so it's going to, left to its own devices, experience exponential growth. Okay, and so we're going to have AV, where you can see that this is like our classic feedback loop where V is feeding back onto itself. The victim's rate of change is proportional to how many victims there currently are or how many prey there are in the system. And this constant of proportionality, A, is going to be a number greater than 0 because this population is growing on its own because it has its own food source. Okay, so where A is greater than 0. That's because the prey has its own food source, right? And now I'm going to contrast that with the predator because in these models, typically what we want to do is say that the predator P is predatoring. I don't know. predating on, it's eating the victims, okay? It's eating them. And if it doesn't have any V's to eat, it's gonna die. BP, so the rate of change for the predators is proportional to how many predators there are, but the difference between predator and prey is that the proportionality constant B for predators is less than 0. That's because left to their own devices with no victims around to eat, they're going to be experiencing exponential decay. They're going to be dying out with no food, okay? And so the easiest way for me to use this as an example would probably be to let A is equal to like +1 and B equal to -1, but I'll just put that up in there for now. And then what's missing here is we need to add interaction. And I think somebody on there had just said that could we have a breakdown of predator-prey and include probability a little bit? And so this is where the probability comes in, because when we're assuming that there's some interaction going on between predator and prey, the rate at which interactions occur is going to be proportional to the product of P times V. So interaction is going to be proportional to the product of the populations. PV. Okay, and that actually originates from probability theory because if you've seen probability theory at all, assuming we have two independent events, A, probability of A occurring is P of A, and B, and the probability of B occurring is P of B, what's the probability of them occurring at the same time? What's the probability of A and B? It's the probability of A times the probability of B. And that's the assumption for independent events in probability theory. Now, the probability of a victim and a predator occurring in the same bit of grass at the same time, and so, you know, that interaction having to actually happen, the probability of predator and prey being in the same place at the same time is proportional to probability of predator times probability of prey, or P times V. You see, because the amount of creatures there are in each category is related to the probability of finding one in any particular patch of grass, assuming that they're all just wandering around independently. Now, really, they're probably not wandering around independently. Really, probably, if a mouse spots an eagle above, it's probably going to hide. But this is also the very simplest way to model interaction. And so there's a good mathematical reason, even outside the realm of probability theory, and that if I want to say, you know, how often these things are going to interact, the most simplest way that I could say that is to just multiply P times V. Okay? And so that brings us to the whole model. And in the whole model, the victim's rate of change is going to be exponential growth. So the victim is feeding back on itself with exponential growth. And then, unfortunately, it loses out. So minus C times PV, it's losing when it meets the predator. So that's why this is a negative thing. Actually, one thing I just realized was it might be better for me to change this to all of the parameters are positive, but negatives are in front of the ones where I want to emphasize that they are negative. Okay, so I'm just going to make a quick change here. I know I said B was less than 0, but it's going to generalize better if I denote negative numbers as negative times a positive number. So I can say where all the parameters are greater than 0. So I'm going to make that quick change there. That's why I've got this here. So C is a number that's greater than 0. All the parameters are positive, but I'm emphasizing that the prey is going to lose out. Its population is going to go down proportional to the number of interactions that happen between predator and prey. And so the equation for the predator is going to be now minus BP. This is the same thing I was saying before, except I pulled the minus out of the B so that I could say all the parameters are greater than 0. But the idea is the same, that the predator is experiencing exponential decay in the absence of prey. But then when it does see some prey, whoop-de-doo, it gets something to eat. And so it has a positive benefit. Its rate of change increases proportional to interactions between predator and prey. And so that's the full general model, also sometimes called the Lochte-Volterra model. And this is the base model that we're going to use for a predator-prey. And then we're going to start to maybe make it a little more complicated. Like realistically, are prey going to grow exponentially forever? No, they're probably going to have a logistic term. So some extensions that we could do is we could add a logistic term here to the growth rate of the victim on its own, or a variety of other things. Anyway, I don't want to overcomplicate it. So there is a review of the predator-prey model. And now to go on to imagining concrete examples. If you are going to say that vector fields is one of your concepts for this week, which it's one of the most important concepts this week is vector fields, an example would be drawing the state space. So there's the victims on the x-axis and there's the predators on the y-axis. And an example of a vector field would be drawing some little arrows all over the place. I mean, not just randomly, though. Go ahead and use that link online to get a visual on that, or describe it with your own words. But you could say an example of a vector field is when I evaluate the predator-prey model inside the state space. And when I do evaluate that model, I get directional vectors that represent the rates of change inside the state space. So an example of a vector field, maybe to pin it down so it's nice and specific, I would say here's an example of a vector field for the predator-prey model at a certain point. And so I would say maybe at the state 2, 3. And then in order to really do this example, if I want to pick a state 2, 3, in order to evaluate the vector field, I'd probably have to put numbers on all these parameters. So when you do your example, you're probably going to have to choose numbers. For me, I'll just choose 1 for all the numbers just to make it easy to compute it in my head. So I'm going to go ahead and let A equal 1. I'll let C equal 1. I'll let B equal 1, and I'll let D equal 1, so that I just let all the parameters equal 1, so I can plug in this point. And here's the point 2, 3. So here's the point in the state space. And an example of a vector field would be me evaluating this at this point. And that's actually like the exercise set that you're going to see this week. So we're getting some good examples of exercises in at the same time. Let's see, V prime would be V minus PV. So V is 2, and then minus P times V, so 2 times 3. So minus 3 times 2. I'll write it in the order that it's seen. You can see I'm plugging in 2 everywhere I see a V, and I'm plugging in 3 everywhere I see a P. And so that's going to be a minus 4. And then P prime, I'm going to again plug in a 2 everywhere I see a P, and I'm going to plug in, oopsies, my bad. I just made a mistake. That's good for business. Mistakes are real. We got to pay close attention to what we're doing. What I meant to do is I'm going to plug in a 2 everywhere I see a V, and a 3 everywhere I see a P. Maybe it'll help me if I do V, comma P, and I just put that right below the 2, 3, so I can remember what I'm doing. Okay. So if I see a P, I'm going to plug in a 3, right? And so I got minus 3 plus 3 times 2, and that's equal to minus 3. So you can see that for this example of a vector field, the vector that I'm going to draw on top of the state space there, I'll draw it in a different color so I can emphasize it. Somebody told me that blue doesn't really show up. Blue shows up, but somebody told me that they can't tell the difference between blue and black on the board. So I'm going to use red for the vector field instead of blue so you can see the difference. I'm going to draw the vector -4, -3 on top of the state space. Okay, so this is going to be a little tricky because it's such a large value. Technically, if I really wanted to draw -4, -3, what I would do is I would start at that black point, and then I would go to the left by 4, and then I would go up by 3. And so I'm gonna, I mean, if I really wanted to draw this to scale, it would look something like that because it's so big. It's -4, so it's going over by 1, 2, 3, 4, and the x, and then it's, oh, my bad. Sorry, I did another mistake on the board. It's -3, so I got to go down by 3. Okay, so I'm going to go -4, -3, -4, -3, and so I'm going to be like right here. Yeah, so what I'm thinking here is that I want to go 4 to the left and 3 down, but I'm starting with the end of my vector as the state at which I evaluated the vector field. Okay, that's why we learned how to add vectors earlier in the course, is because you can think of this as me trying to kind of overlay this vector on the current state. I don't really want to say that I'm adding them, though, because I'm not really adding them. They don't even have the same units, right? The state 2, 3 is in units of like number of squirrels and number of wolves. And then these rates of change would be like -4 squirrels per month and -3 wolves per month. And so you don't want to think about that you're actually adding them, more so you're overlaying them. Great. And so people are saying that this is helping them. That's good. Thanks for the feedback. I really appreciate that. So that's my example of a vector field. Now, if you were going to share an example of a trajectory, you could say for the predator-prey model, as we saw in the videos, a lot of the trajectories are these closed, sort of circular. They're not exactly circles, but they're these closed loops in the state space. And so those are all examples of trajectories. For your concept post, you're not expected to upload an image or anything. And so you wouldn't really need to upload an image. And you wouldn't even really need to showcase this much work because you don't have to type in that much math. But you would just kind of explain this process in your own words. Why don't we complete this by talking through a little bit of Euler's method. I know I didn't make a chalk talk for Euler's method. I went straight for a video that illustrated me using the online tool that I had presented. But I think it might be beneficial for some people to see me iterate an initial condition using Euler's method so that we start to draw out a trajectory in the state space. So this would be an example of applying Euler's method. And if you did in your discussion post want to type out that example, then you could follow it up with typing out this worked out example of Euler's method, if that was another one of your concepts. But I hope people aren't feeling too hung up about the concept discussion. Really, the vision that I had in my head was a check-in early in the week so that people are engaged and that they know what's coming and then they're not saving everything for the end of the week. So it was an encouragement for you to do your readings early, and it was just a bit of a check-in there. And so hopefully you feel like that's not too much work, but it's supposed to be creating a new resource for us so that we're sharing our the concepts in our own words as well. Okay, so I'm going to iterate this with Euler's method. Okay, and so what Euler's method tells you to do is that you're going to start wherever you start. Let's say that we have an initial condition. Initial conditions are usually abbreviated with IC. And so by IC here, I mean my initial condition is 2, 3. Okay? And then in order to complete one iteration of Euler's method, what I'm going to do is I'm going to, so this is like step 1 is evaluate the vector field at the current state. Okay, so the first step you're going to do is you're going to say, okay, if I'm starting here, this is where I start is 2, 3, I want to see what my rate of change is. And I already did that part on the board over here. And so the evaluation of the vector field using that initial condition of 2, 3 is that v prime is equal to -4 and p prime is equal to -3. Okay, so that's step 1. Hold on. I want to give myself enough space to do the rest of it. So where'd my eraser go? Let me just erase that. You already see that over there, so I don't need to do that again. I want to write step 2, make sure I have enough space. And step 2 is you're going to multiply the rates by the time step. And so you'll see in the exercise sets that when they ask you to iterate Euler's method, they're going to tell you a time step. The time step is sometimes referred to as delta t, or on the online software link that I made my 1.7 video on, is denoted with an H. Typically, that's going to be given to you if it's asking you to do an exercise, or if you're doing real-life research or something, then you're going to need to pick an appropriate value for that. Almost always a value less than 1, usually like 0.1 or 0.01. And there's always that balance between how much computational effort you want to do and how precise you want it. So a smaller delta t is going to give you a numerical approximation that is closer to the true solution. The smaller the delta t is, the closer you'll be to the true solution, but the longer it's going to take. And what I just said there is kind of the answer to one of the exercises in 1.7. So hopefully that helps you there. So let's just set delta t is equal to 0.1. That's just a classic thing to set it as. Sorry, I'm just coughing because I've been talking so much. If you have bared with me, you know that I've been talking for almost 3 hours straight now. I'm getting a drink of water live on YouTube. Okay, so that's better. I've got my delta t set. That's step 2 is I'm going to multiply the rates that I found here times that. So let's see how I'm going to write this. So I'm going to take v prime is equal to -4. And so v prime times delta t is equal to -0.4. Okay, and likewise, p prime is equal to -3. And so if I multiply p prime times delta t, that's -0.3. Okay? The reason that you want to multiply those is because v prime and p prime, we'll see this more in chapter 2, are really also known as delta v over delta t and delta p over delta t. So I'm just going to write that on the side. We're going to start to get introduced to that other type of notation pretty soon in chapter 2. But v prime is also known as delta v over delta t. And likewise, p prime is also known as delta p over delta t. And the reason that I want to bring that up right now is because you see me multiplying v prime times dt, times delta t. And if v prime is also the fraction delta v over delta t, and I multiply that by delta t, what I'm going to be left with is just the numerator, delta v. And likewise down here, I'm multiplying delta p over delta t by delta t, so that is actually delta p. And what the delta means is change. That's the amount of change in that one thing. And so for my final step, step 3, is I'm going to move my state by the change amount. The change. Delta p or delta V. Okay, and so for my final step, once I've computed delta V and delta P, I'm going to make my move. I left this up here because I think it's helpful to consider what I'm doing visually. So here we already have the state space. We have the vector at the point 2, 3. And then for my final trick, what we're going to do is we're going to say, how far did we move? We started here, and we walked along this line for time is equal to 0.01. So we didn't walk along this line forever. If we had walked along this line for exactly 1 time unit, we would have made it all the way to here, the end of the vector line. See, that's if I walked along the red line, the vector, for an entire 1 of delta t. So if my delta t was 1, you see I would have got -4, -3, and I would have made it all the way over here. But that's not how long I walked. And so I made it to about here. See, I went from here to here, and I moved along this line for 0.1 time units. Okay, and so if I moved from there to there for that long, really I got right here, that's what I'm doing in step 3, is now I'm making the move of my state just for that long. And so my new state is, let's see, I was at 2, 3, so 2, 3, plus the change, -0.4, -0.3, which is to say I was at my original state, which is V, P, plus delta V, delta P, and it's more space here. So where did I end up? Now this is really why we learned to add vectors, because properly this is a sum of where I am, number of squirrels, number of wolves, plus how far I moved in the same units. Now this is in the same units as the state, because you see I multiplied away the per time part of the unit. Remember when I said that V prime and P prime are like number of animals per time? If I multiply number of animals per time by an amount of time, then I'm back into number of animals. And so now here I really can properly add these things together. And what I get is 1.6, 2.7. And that's my new state. So step 3 is to get your new state by adding the change to wherever you started. And there's the visual of it right there. And so my one single step of Euler's method led me to believe that at time equal to 0.1, P, V is equal to 1.6, 2.7. Oops, I did it again. I meant V, P. Sorry about that. V, P. And the reason I'm saying that that's happening at time is equal to 0.01 is because that's my time step. My delta t was 0.01. Now, if I wanted to know where this system was going to be at time is equal to 0.02, I'd have to do the entire process over again and start with step 1. But in step 1, I would evaluate the field at this current state. So I would take these two numbers, 1.6 and 2.7, and I would plug them into the state equations for V prime and P prime, multiply the output by the delta t, and then move the state accordingly. And I would do that over and over and over again as time progressed. So if I wanted to know what was going on at after one whole time unit, I'd have to do this process 10 times. If I wanted to know what's going to happen after 20 time units, that would mean that I had to do that process 200 times. Tedious, yes, but in the age of computers here, we're really going to have the computer do it for us, which is great because you really do, for Euler's method, need to take a teeny step to get an accurate depiction of the true solution. One thing that I really want to emphasize is that numerical computational simulation of a model, it only approximates the true solution. The true solution lives in this infinitesimal world of calculus, and that's what we're going to travel to next week as we start to appreciate what the actual B prime and P prime mean, because these are known in the calculus world as derivatives. And derivatives kind of have this concept of being an eensy, teeny tiny step. And so when I over here took this big chunk of a step, 0.1, that's just an approximation to truly what I was trying to say, which is an infinitely small step. So numerics can only get you so far. And in fact, numerical analysis is like a whole branch of mathematics, because we have so many different ways to model, different strategies to model complexities, and then we usually don't have the answer to any of our models. So our only hope is to ask computers to help us crunch through, to think up new ingenious algorithms that are going to make good approximations to the solutions. And that's a whole branch called numerical analysis. Cool. I hope that was really helpful to you all. I think we're nearing the border of 2 p.m. So hopefully that answers most of the questions or things that were on people's minds. And keep going with the class, and keep letting me know how you feel, because feedback is the name of the game. And I really appreciate your feedback. I'm always looking for which ways that I can support you. And so thank you too for being here, and thank you for working with me as we go on this adventure in learning. And I'll see you on Thursday. Bye.